So we've been looking at the relationship between rectangular and polar coordinates, rectangular equations and polar equations, and the curves. We've learned how to graph curves that are given to us in polar form. And we've also learned how to find slopes of tangents when we're given y equals f of theta. R equals f of theta. In other words, something of polar form, we've learned how to find slopes of tangents, dy dx. Now we want to bring in integrals into this. And to begin with, I want to consider a circle. Okay, so here's just a circle of radius r. And I want to do this. I want to say, okay, this angle here, we'll call this alpha. This angle here, this is beta. And I'll call this angle in here just delta theta. I can call it anything I want. I'll call it delta theta. And notice that delta theta is just beta minus alpha. I'm doing that because hopefully when I make this transition in a minute, using delta theta will help us. But now, if I want to find the area of this sector, okay, this sector right here, if I want to find the area of that, well, one of the things we learned back in geometry was we learned that the total area of a circle is pi r squared. This is not the whole circle. This is a fraction of a circle that has 2 pi radians. So if the whole circle has 2 pi radians, and I look at the number of the radians that I have, that's the fraction of the circle that's of interest. So notice these pi's cancel, and what we have is we have r squared over 2 delta theta. This will give us the area of that circular sector. Okay, now remember back when when we were just being introduced to integrals. What we learned was, we said, well, consider a function like f of x equals x squared on some interval. And we were told, divide that interval up into 3 equal parts and use that to approximate the area into the curve. So notice, I found delta x by taking the width of the interval, dividing by 3, and I got 2. And then we divided up under the curve. We said, okay, here's 2, 4, 6. And then I just made rectangles, okay? Rectangles. And we said, okay, we're going to add up the area of those rectangles. That's going to make a sum, and we'll use that sum to approximate the area under the curve. And this is the way we've defined definite integrals. So we had a curve, because we knew how to find the area of a rectangle. I know how to find the area of a rectangle. It's just delta x times, f of 6 in this case, or 2 times f of 6. And then we said, well, let delta x go to 0. In other words, let there be infinitely many rectangles. And we found that limit was our definite integral. Now, what I want to do is I want to take a similar approach. Let's suppose that we have some kind of curve. Okay, some kind of curve, and let me just draw it here. Okay, so I've got, okay, let's suppose this is a curve that we have, and it's a curve that came about from us sketching this, r equals f of theta. Now what I want to do is I want to figure out what is the bounded area in this curve. Or let's suppose I just want the bounded area over part of it. Let's suppose I want to go from this angle, from this angle alpha to this angle up here beta. Okay? Let's suppose that's what I want. Well, so just like with when we were first introduced to the integral, we want to use what we already know. We know how to find, the area of a circular sector. So maybe I'll go up here and get a little, I'm not good at drawing this, but maybe just think about a circle. Okay. Now this is not going to be exact here, right? So what I've got in here, I've got delta, let's say this is delta theta 1. And I pick some value r that's on my curve, so maybe r1. Okay. Now, if I want an approximate area of this wedge, it's not going to be exact, I can do this. I can say delta theta 1 over 2 r1 squared. And that will give us an approximation for this little sector here, okay? Just for this little sector, just for this. And then I can do the same thing for other sectors. I can say, well, I'm going to keep going with this then. And every time I do it, I get another little approximation, right? That's not exact. So I get delta theta 2 over 2 r2 squared. And I keep going until I go all the way from alpha to beta. I do that for theta equals alpha to beta. And I add up all of these little things. Now, let's think about, what if I let theta get infinitely small, infinitesimal? Let's just let theta go to 0, this delta theta. In other words, these little wedges get, the difference in the angle, the delta theta here gets smaller and smaller and smaller. Well, that means I'm getting more accurate with my approximation here. And in fact, what if I say, well, let delta theta go to 0? Well, if that happens, then we've got a Riemann sum. And what we have is a situation where we're going from alpha to beta. We have 1/2 r squared d theta, like that. Now, this is the formula that we're going to use in integrating and finding bounded areas like this. This is the formula that we use. Okay? Now, let's see this in action. Let's see how this would actually work. Let's suppose that we have r is equal to 3 cosine 3 theta. Let's just suppose that we have this one. And let's suppose that we want to find the area of one of the petals of this graph. Now, so let's look at the graph first of all. Let's see here. We've got 3 cosine 3 theta. Okay, let's suppose we have this, and I'll just set my window, I'll just set my window that way for now. Okay, so there's what it looks like. In other words, what we want is we want just this one petal, okay, one of these petals. Now, let me cut that out and put it in. Okay, so let's take a look at this. Okay, so this is what we want. Now, so here's what I'm interested in. I'm interested in this area of this petal right here. Okay, so here's the way we would set this up. I could say, okay, I know I'm going to integrate. I'm going to have 1/2 the integral, and I don't know what my bounds are yet, but I do know that I have r squared. So this would be 9 cosine squared 3 theta d theta. Okay, there's my integral. There's my integrand, right? Okay, because this is just r. This right here, this whole thing is r, and remember it's 1/2 r squared d theta. Now what I've got to do is I've got to figure out what my bounds are. Now if you notice what this r does, r goes this way, right? When the angle is 0, it's out here at 1, and then it goes like this, it goes like this, but notice that you get back to 0, right? Or the radius gets back to 0. So here's the radius, and you'll notice it starts here. So what we want to do, here's what we want to do. So you start here, and you get back, you keep going, and the radius gets shorter and shorter until it gets to 0. So what we want to do is we want to figure out, well, where is that radius 0? Okay, and that's going to give us half of this. Okay, so let's see what we've got now. We want to know, well, where is the radius 0? Right here. So it starts off here, it gets shorter, 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 and then it's 0. So that's going to give us some idea about what our bounds of integration. So let's do this. Let's take 3 cosine theta. cosine 3 theta equals 0. And let's see what this looks like. This gives us cosine 3 theta equals 0. Now cosine equals 0 at pi over 2. So this is going to be pi over 2 plus k pi. Because it's at pi over 2, 3 pi over 2, 5 pi over 2, so forth. Okay, so let's take a look now. Now I'm going to divide by 3. And theta equals pi over 6 plus k pi over 3. So I'm thinking that this thing gets, the radius is going to be 0 whenever theta is pi over 6. Now that's important for me because let's just see what this looks like. Let me go back to my calculator and let me just graph, instead of from 0 to 2 pi, let me graph from 0 to pi over 6. Ah, it looks like I have the top part of that. Now, if you think about it then, if you go back to the expression, okay, if we let k be -1, we get pi over 6 minus pi over 3, and that would be negative pi over 6. So it seems plausible that we want to go from negative pi over 6 to positive pi over 6, and that's going to give us this little pedal. So let's see if that works out. We can always try it. We don't have to trust ourselves. So we go negative pi over 6. Okay, and there it is. That's the pedal. That's the pedal we want. So now also another thing, notice there's some symmetry here. So maybe I don't want to go from negative pi over 6 to pi over 6. Maybe I want to utilize the symmetry and do this. Maybe I want to go, I have 1/2, and here is 3 cosine 3 theta squared d theta. Maybe I want to go from 0 to pi over 6 and just double it. Maybe that'll work. I think it will. Okay, and that might make it a lot easier on us. So let's see what we've got now. We've got 0 to pi over 6, 9 cosine squared 3 theta. Okay, so the 9 just came from me squaring this 3. Now remember how we integrate cosine squared or sine squared. We use an angle reducing formula. So here we've got 9, 0 to pi over 6. This is going to be 1/2, 1 plus cosine 6 theta. There's what it is. And then I can factor out the 1/2, and I get this. Here's what I get there. I get 9/2, 0 to pi over 6, 1 plus cosine 6 theta. And then I can integrate. I can just find the antiderivative, which is easy, because this is theta. Now the antiderivative of cosine is sine. Divide it by 6. Got to remember. Okay. And I'm going from 0 to pi over 6. Now, it's just a matter of plugging in now. So we've got 9/2. Let's see what we've got. If I put in the pi over 6 here. Now, if I put in a pi over 6 here, that's going to be 6 times pi over 6, which is pi. That's 0. Okay? Sine of pi is 0. Okay? So I've got this minus. Now if I plug in a 0, I get, once again, 0 plus 0. So it looks like my answer is going to be 9/2 times pi over 6, which is, let's see here, this is 3 pi over 4. Looks like it reduces to that. And that's how we do these integration problems.